Okay, gentlemen. Now remember your homework. I want us to do a couple of lessons at home, and that way we can get a few extra lessons to do experiments and investigations. Because you guys are gone halfway through week 4. I think you guys are getting ready for your venture. Now, this was what was covered in the Year 11 videos that I asked you to watch over the weekend. If we had an object on an incline, the thing about an incline is that the normal force only acts perpendicular to the surface, and it's actually opposing the perpendicular component of the weight force. And so the perpendicular component of the weight force is mg cos theta, and so our normal force can be rewritten as mg cos theta. If it's on a flat surface, then cos of 0 is 1, and it simplifies to simply mg. You don't have to write mg cos 0, you can just write mg. However, if we ignore friction, so really I could have put a couple of wheels on this box here and suggest that friction doesn't act. If these are the two forces, then they are not balanced. And if we did a tail to top diagram, I didn't draw a tail to top diagram. If I drew a tail to top diagram and drew the weight force acting down, then the unbalanced force, the sum of all forces, points down the incline. So it turns out that it's actually parallel to the incline, right? And it has the magnitude mg sine theta, okay? So just be careful. I like to trick my Year 11s and 12s by asking them to draw all of the forces acting on the object. And a common mistake that they do is that they draw in that and write mg sine theta. That is not acting. That is not a force. It's the vector sum of the other two. So that's the correct answer. Those are the only two forces that are acting. However, if I draw in the weight force, there's our weight, there's our normal, that is the unbalanced force, and that has a magnitude of mg sine theta, which makes sense. Again, if we set the incline to 0, then there is no unbalanced force. We can say that the force down the incline is mg sine of 0, which is a big fat 0. Or if we made the incline 90 degrees, imagine I drew an incline of 90 degrees and I put my object here, there is no normal force. The force down the incline is mg sine of 90, which is just mg. Okay? So you can analyse it at both extremes, on a flat incline, on a vertical incline, and for any angle in between, we can summarise our statements here, that the normal forces, and by the way, the weight force is always mg, it always acts, it always points downwards. It's only when it's level that it puts the object in equilibrium. If we put it on an incline, they no longer balance. Okay? Friction might be able to balance it, but for this example, I just said, suppose that this was a cart on a track. If you tilt the cart, it's going to start to accelerate down the incline. Again, always down the incline, always parallel to the incline, always at the same angle, theta, which makes sense. You don't ever take an incline track and lift it up and the cart suddenly flies up into the air or sinks down below the track. No, it accelerates down the incline at the same angle of the incline. All right, let's get to today's lesson. The aim is that we can get this booklet finished and you guys can attack the questions that are at the back of the booklet, because there are lots of them and they are fun. Now, we played around with this apparatus last week. It's called the Atwood apparatus. We used this to confirm Newton's second law, that the acceleration was directly proportional to the unbalanced force, and that it was the unbalanced force, it was the weight force of this hanging mass that produced an unbalanced force. Okay? Now, what we're now going to do is calculate all of the forces that are acting on these objects. So let's suppose we had a 5 kilogram mass on the track, and we had a 1 kilogram mass hanging over the pulley. For now, we are going to ignore the weight of the cables. Okay? We would say that the unbalanced force, we'll call him M1 and we'll call him M2, it's the weight of the hanging mass. And in this case, it's 1 by 9.8, which is 9.8 newtons. Okay? Now, what we're going to have to do is suggest that that unbalanced force acts on the mass of the system, the entire mass. We've got 6 kilos of stuff here, and there's an unbalanced force of 9.8 newtons acting on that 6 kilos.
Can you give a direction for this?
No. I'll tell you why in just a moment. Okay? So could we just write here, the sum of all forces acts on the entire system, which we will call M subscript S. So we can say that the sum of all forces is 9.8 newtons, which is the mass of the system times the acceleration of the system. That's Newton's second law right there. So we can figure out the acceleration of the system. It's going to be the sum of all forces divided by the mass of the system. 9.8 divided by 6 kilos, we get 1.63 meters per second squared. Okay? What that means is that this object up here will accelerate that way at a rate of 1.63. And this object here will accelerate downwards at a rate of 1.63. Okay? We have this very special machine attached to the edge of our track, which is able to change the direction of the tension. Okay? So if I said, let's draw all of the forces acting on the cart, I could say, well, there's a weight force down of 49 newtons. There's a normal force up that must be equal and opposite, must be 49 newtons. But now we've got this tension force. So there's a tension, there's a pulling force through that string, and it's acting on that 5 kilo mass to cause that acceleration. Okay? And we're going to look at these in separate scenarios. If we looked at mass number 2, I could say that there's the weight force of gravity pulling that object downwards. And then there's a tension force upwards that's pulling it up. Okay? So now, there's a little trick with this Atwood machine. First, we've got to treat it as a system to figure out how the system behaves. You would see it start to accelerate. If we just watch the top mass, we would see it accelerating to the right, and if we watch the hanging mass, we would see it accelerating downwards. But, providing that this is a rigid rope, it's not elastic, it's not a slinky, it's a taut piece of rope, they are going to accelerate at the same rate. Okay? They're going to change their velocity by the same amount every second. Now, up the top here, what we're going to do is we're going to analyse both. The tension is going to be the same magnitude. So whatever the tension is, acting on each mass, it's going to be the same value. So let's just look now. I'm just going to highlight mass number 1. I'm going to draw myself a little box here. That should hopefully be enough. Up here, I could say the following statement, that the sum of all forces acting on mass number 1 is going to produce an acceleration, and the unbalanced force is tension. Okay? We can essentially ignore the vertical forces because we know that they're balanced. So I can say that the unbalanced force is tension, which is mass times acceleration. All right? Well, we've been given the acceleration, so it simply becomes a nice, easy 5 kilos seen to accelerate at that rate must equal tension. And so what we get is 8.15 newtons that way. Okay?
Is tension a vector?
Yes, it is a vector. But here's the funny thing. The pulley changes the direction. And also the direction changes depending on what objects it's acting on. If I said, what's the direction of tension acting on M1? It's that way. If I said, what's the direction of tension acting on M2? It's upwards. Here's another, here's a very easy, think, Mr. Murray, think. Not very good at doing that. Okay, oh jeez, what the hell is this? Oh God. Right. there's tension through these ropes, right? Just imagine it's one rope. If I said, what's the tension acting on the box, you would say it's so many newtons upwards. But then that tension's also acting on my finger. If you said, what's the tension of the rope on my finger, you would say, well, it's the same number of newtons downwards. So that's the weird thing about tension. It depends on the object. So sometimes in the question we'll just say, calculate the tension in the rope. You could just put the magnitude. If it says calculate the tension acting on the mass, then you can add the direction. So I already automatically know that the answer down here is 8.15. But let's show it. Let's prove it. So down here, I'm going to do another working out box. You might not want to do that because you might write a little bit larger than myself. All right, down here for mass 2. Mass 2, it's a little bit more complicated because there's two forces acting here to produce the unbalanced acceleration. I could say that the sum of all forces acting on mass 2 is weight plus tension. So there's two forces, two vectors on that diagram, and that produces our acceleration. Now here's where we need to be careful. Now we've got tension acting up. I'm going to assign that tension is positive, and I'm going to assign that weight is negative. Which way is this object accelerating? Downwards. Yes, so we're going to have to write up here, apologies for not writing it sooner, I'm going to write negative.
But then you're going to have to get rid of the down arrow.
Good point, a double negative. That's right. Yeah, there we go. Negative 1.63. But remember, we never express direction with signs, but for now, we'll just leave it in maths mode. So, we could plug all the values in now. I could say that 1 by negative 1.63 equals negative 9.8 plus t. Again, you'll see there that that value assigns the direction, and so does that value. They need to be there. What this is saying is that this object's accelerating downwards, there's a downwards force of weight, and there's going to have to be an upwards force of tension to make this work. I could simplify this and go negative 1.63. Okay. What this is saying is that all of the forces acting must sum to negative 1.63 because it's causing a 1 kilogram mass to accelerate by that rate. Well, weight is already providing 9.8 down. We only need 1.63 down, so the tension must have the remaining upwards. And what did we say it was? It was 8.17. Which should be 8.
Well, it's a sig figure of gravity, which is 9.8.
You're right. Sorry, okay, how about I do this? And then it should hopefully... What about 1.5?
You rounded to 1.63.
What happened up here?
See the 1.63?
Yep, what should it be?
Oh, I'm not sure. It's just...
Does somebody want to check? Yeah, how about me? 9.8.
I think it's the rounding before that.
1.63, okay, and then times that by 5. 8.15. And
Because you rounded acceleration.
9.8.
So do a lot of threes and see what happens.
If you sub in...
You're right.
tension at acceleration.
What should it be? 8.17. Okay, it really should be the same, but we'll write that up to a rounding issue. Okay? Let's just go back to this. If I held this object, imagine I came up with my finger and held the cart with my thumb. Thank you. What would the tension be?
0. It's not accelerating.
Who could tell me? You use your logic, use your...
We just grab this.
If I put my finger here, what would the tension be?
It wouldn't change.
Ways of moving.
0?
It
The
wouldn't
mass is still hanging there.
It wouldn't change.
Will? 9.8. You're absolutely correct. What that would do, it would keep everything in equilibrium. This object here would not be accelerating. In which case, that equals 0. So tension and weight must be equal and opposite. Well, if you've got 9.8 down, then it must be 9.8 up.
Unless you
Okay.
can't hold 9.8, so.
Which means I could then add, if I had my thumb there must be a backwards force of 9.8. Basically, by putting my thumb there, I have to withstand the weight force of the hanging mass with a backwards force. Well, my thumb, friction between my thumb and the cart. I would probably have to press down, so there might be a downwards force, so the normal force would increase. Everything gets a little bit trickier, but I just thought I would bring in that scenario. Let's go to a slightly more difficult scenario. Well, it's not too bad, but I'm going to have to assign my conventions here. Let's go that the angle here is 25 degrees. We have a mass, it's the same mass, 5 kilograms. And just to muck things up, we'll say that M2 is 2 kilograms. Okay? It will work. Well, now here's the thing. What we need to find out first, this is like a tug of war, okay? There is going to be a tension this way, and there's going to be a tension this way. You've got your weight force down, and now I'm going to combine, we've got weight and normal, and I'm going to summarize that as the force due to gravity, which is mg sine theta. All right? Now a quick little check. Whichever one works, whichever one is larger is going to win this tug of war. And so if this weight force of the hanging mass is greater than the force down the incline, then he wins. Well, he's going to be 19.6 newtons. This guy here is 49 sine 25. We'll do a quick little check in just a moment. Okay. What I'm going to do is assign. Let's just quickly sketch the two masses. You've got M1 being pulled this way with T1 and this way with force due to gravity. You've got your hanging mass, which is being pulled, well, look, you can draw it like that if you want. You've got your hanging mass, which is downwards weight and upwards tension. What I'm going to do is I'm going to contract this into one object. I'm going to call it the mass of my system. And I'm going to say that this way is weight 1, which is weight 2, which is M2 times gravity. And this way is the force due to gravity on cart 1, which is M1g sine theta. So it's a tug of war by the two objects. Yep.
Given that the tensions are the same.
We can ignore the tensions because they cancel each other out. If imagine bringing these two masses so that they were just over the pulley, and you've got a force that way and a force that way, it's a very simple tug of war.
So would the tension on mass 2 be the same as the force due to gravity on mass 1?
No, the two tensions are the same, but they're not going to be balanced. We've got to figure out which way this thing's accelerating. Let me assign a convention. Let's say that down the incline is positive and the weight force is negative. This is a little bit of a trick. We've assigned a convention. We know that they're opposing each other, so we're just going to see which one wins and by how much. We want to find out what the unbalanced force is. So I'm going to write that the sum of all forces is I'm going to add them, M2G. So I'm going to get positive 20.7 No, we'll use our decimal rules. This is no, actually we won't.
Aren't there like?
We'll write down below horizontal. Hang on.
Aren't there two directions it could be if you wrote 25 degrees below horizontal?
Yeah.
Left.
So why is it? Oh, okay, yeah.
But that doesn't work for the person that's looking on the other side of the projector screen. They would see it right. Now, if you know what I mean. Someone could do over an NP for looking at the back of the screen. So I'm happy if you just wrote below horizontal. What I've just said here, gentlemen, is that the the force down the incline on this mass is greater than the force downwards of this mass. He wins the tug of war, and he wins by 1.1 newtons. Okay, that is the unbalanced force, and we would see the cart go down the incline and the hanging mass raise upwards.
And then will we find the acceleration by doing 7 on the 7 divided by the unbalanced?
Yes, you're one step ahead of me. Yes, that's exactly what we're going to do now. Now we can figure out the acceleration of these two objects. It's the force divided by the mass of the system. So it's the same step as before. So that was sort of step 1. And then step 2, we can find the acceleration of the system. Our 1.1 divided by our 7 kilograms gives us 0.16 meters per second squared. Now that's just the magnitude of the acceleration, because we know that cart 1 is accelerating down and mass 2 is accelerating up. And that's when we need to again assign our conventions. Now, we're going to solve for tension on both of them. So what I'm going to do is I'm going to split my page into 2. But really, you would only have to choose one and solve. I'm just going to show you. Solve for T on M1. I'm going to draw a little scenario. Here's my 5 kilos. Here's my mg sine theta, and there's my tension. And that obviously acts at an angle of 25 degrees. Now, again, I'm going to have to assign convention. I'm going to go that down the incline is positive and up the incline is negative. Okay? Which way is our acceleration? Down the incline. So we're going to go plus 1.6. 0.16, thank you. Okay. Thank you. We make our statement. Newton's second law says that the sum of all forces acting on one is the combination of Fg1 plus T, and that produces our acceleration. We're going to plug everything in. We'll go that 5 by 9.8 sine 25 plus T equals 5 by 0.16. I've got written here that 20.7 plus T equals, and now 5 by 1.6 is 8. 0.8, is it? 0.8. Yes. Therefore, T equals 0.8 subtract 20.7, which gives us what? Negative 19.9 newtons. Or 19.9 newtons up the incline. Again, have a think. We can vary the tension, and that's what you can do. You can change the matter. We can vary the tension. At the moment, my tension is less, and so gravity is greater, and so the unbalanced force down the incline. It's less than 20. That's all the mass can make. The mass can only make 20.7. So if I made T less than 20.7, it wins, and it goes down the incline. If I made tension greater than 20.7, it loses, and it would accelerate up the incline. Well, we could do that. We could throw more mass on our hanging mass. I could throw 40 newtons on our hanging mass, and then it's 27 and 40, and the thing's going to accelerate up the incline. I could make it equal to 20.7, and then what would happen? It wouldn't accelerate. It could either be stationary, or I could give it a little bit of a tap, and it would start drifting at a constant speed because it's in equilibrium until it smacks into the pulley or falls off the table. One of those things will happen. Yes?
Is there any way to measure the object's acceleration straight down when it's going down the incline? Because I think if you graph the height, just like the height above ground level, would it be different to its acceleration down?
There's different things that we could do. We could film this with video physics and get our dots. We could we could pass it through a photo gate, which is a special laser beam, and have two different gates, and it measures the speed through one gate and then the speed through the next gate, and by telling the difference in speed over time, you can figure out the acceleration. What we did on the day was we measured how long it took to travel half a metre, and then used the equation A equals 2s on t squared. So that would be a cruder way to measure the acceleration over that distance. So we know that the answer is 19.9. Let's just prove it by solving for t on m2. I'm going to draw now my hanging mass. I've now got my weight 2 and my t. We need to assign a convention. Weight is negative, t is positive. And what way was our acceleration? Try again, it was upwards. So again, we're going to have to say that this guy is positive. So again, you've got to really treat it as a completely new scenario because our directions are changing depending on what object we're looking at. So I make my Newton's second law statement that the sum of all forces acting on cart number 2 is weight plus tension, and that causes mass times acceleration. So I can now write that my negative 19.6 plus t equals 2 by 0.16. And what do you think we get? 19.9. And it's positive. It has to be positive because in this scenario, the thing's accelerating upwards, so our tension has to be greater than 19.6, but only just a little bit to produce that acceleration. Okay? So hopefully we've just confirmed that our answers are correct. Okay? Now there's different variations of Atwood machines. I would say that this one is easy Atwood machine. This one is hard Atwood machine. The following page is going to be the intermediate one. I really should have put this in between the two, but oh well. There was a test question a while back in the year 11 test. It might even be year 12. No, I think it's year 11. About a monkey that jumped onto a pulley system, and on one side of the pulley system was some lovely bananas. There's my bananas. Okay, just a slight amount of bruising. And there were it was a 3 kilogram box of bananas. Now the monkey jumps onto the pulley with his 4 hands. And the monkey has a mass of 4 kilograms. So obviously, I could give this to a year 7 and go, what way is the system going to, well, the monkey's going to go down and the bananas are going to go up. Yeah, because the monkey's got more weight. Obviously, if I asked you to draw your weight 1, t, and weight 2, okay? I would ask that you do this now. You can follow all of those steps, and I know that Tristan was already on it. What we need to do is imagine that we could place the mass of the system up here, and it's got a system mass of 7 kilos. We would have a force this way called weight 2, and a force that way called weight 1. That will enable you to find out the unbalanced force and the direction that our system's going to accelerate. Okay? You might need to assign a convention. Let's just say that the banana weight is positive and the monkey weight is negative. Doesn't really matter which way you assign your convention. The monkey's going to win out by a kilo's worth of mass.
So what are we trying to work out, sir? Acceleration.
Well, yeah, but in order to do that, we've got to find out the unbalanced force.
Oh yeah.
It's just one lot of 9. It's 9.8 newtons.
Negative 9.8 newton.
Well, again, it doesn't matter which.
Yeah, but then one of the weights is negative.
Yeah, I mean, I could have put a negative in here for gravity, and then we would have got a double negative. We get a positive. Doesn't really matter. What did I say? Oh, hang on. That one's positive. This one's negative. Doesn't really matter. What do we get? 1.4.
Would it be 1 if it's only 1 and 2?
Okay, yeah, sorry. Let's just, okay, you're right. I'm lazy. Let's just say that it's 4.00. And 3.00.
Negative 1.40.
Then it would be 1.40. So again, now we can split it up. I would ask you now to find for me the tension on the monkey side and the tension on the banana side. Okay. The bananas are going to accelerate upwards, so they have a positive, and then the monkey is going to accelerate downwards, and so would be negative. And that's an important one, because if you forget that, then it's not going to work. So could I ask for you, please? Solve for tension on both sides. Negative 4 plus, what was that, 5.6? I think.
So on the weight and the acceleration going in the same direction for everyone.
No, the monkey is accelerating downwards.
Isn't that where his weight's going then?
Yeah, but if the only force acting on the monkey was its weight force, then the acceleration would be gravity, would basically be free falling. But he's not. there's got to be an upwards force to kind of reduce his acceleration to 1.4 downwards. Okay. Another way to think of it, Tristan, his weight's 39.2 and this weight is 29.4. Now, if the tension is in between those two numbers, he's going to accelerate downwards because his weight is greater than T, and the bananas are going to accelerate upwards because the T is greater than the weight.
Yeah.
The weight's less than T. Yeah?
Yeah.
So you can almost, a quick little check is by looking at this scenario, I know that tension has to be in between both of the weight forces. It's going to have a magnitude between 29.4 and 39.2. Okay?
Would it be exactly halfway?
Well, no, it depends on the rate of acceleration.
So if the acceleration was 1, would that be where it's
There is an equation. Let me just have a quick think. I'm going to answer Tristan's question, or attempt to, over here. Let me just have a quick think. Our sum of all forces, which is M1 plus M2 outside of A, which equals M1G plus M2G, which is M1 plus M2 outside of G. No, that doesn't work.
But their weight forces opposed, so they don't sum.
Yeah, they're in opposing directions. It's subtract. So A equals M1 take M2 over M1 plus M2 times G. So that becomes, I think there's a nice little simplified equation. What would that be? You would get 4 take 3 over 4 plus 3 times G, or 1/7 gravity. Is that what the acceleration is? Yeah, 1.4. So you can simplify it to that expression if you wanted. Thank you for spotting that, Marcus Handley. I would have been scratching my head for a few seconds.
You're welcome.
So it does simplify to that. Now have a look. If they were equal masses, the top M1 take M2 would be 0. Yeah? If it was a 4 kilo monkey and a 10 gram box and a single banana of 100 grams, meaning that this guy is much, much greater than that guy, then it almost becomes M1 on M1 times G. It's almost gravity. If a maths teacher could explain this function better, you kind of get a bit of an asymptote. It'll never be equal to 9.8, but it can become close. You kind of, if you plotted M...
Unless there is no mass 2.
Which, well, that would just be the monkey jumping on an empty rope. In which case, he does accelerate. Yeah, so you could sort of plot that, you could plot a bit of a curve here that you're going to get, it's going to asymptote. It'll never be greater than 9.8 or less than 0. That's a bad curve. I don't want to. I'm going to delete that from the records.
If M2 is 0, then it can't be 9.8.
Yeah, if M2 is 0, then it's not an Atwood machine. It's just a monkey falling. Yeah, there is no pulley. There is no box of bananas. It's just there's a monkey. Look at him accelerate downwards at 9.8. Okay.
I don't think that's ethically.
These are all purely theoretical. Quick, 8 minutes. Let's get this booklet done so you can all do some homework. You've been chomping at the bit to get some homework done.
Yeah.
Heck yes. Now, I just needed to bring this back. Shh. Settle down. Rob. I just needed to quickly remind ourselves, we've already looked at the normal force. It is a reaction force. It's Newton's third law, and it enables this person to maintain equilibrium. If he's standing and not accelerating, we can say weight down equal and opposite to normal up. Okay? However, remember, gentlemen, that your weight is locked. I'd like you to draw a padlock. That your weight vector is always your mass times gravity. It never changes and it's always acting down. So, if we wanted this gentleman to accelerate upwards or downwards, if we wanted to produce an unbalanced force, we would need to vary the normal force. So if we want to accelerating him up, bad English, if we want to accelerate him upwards, we can increase the normal force and he would accelerate upwards. If we wanted to what's wrong with me today? If we wanted to accelerate him downwards, we could reduce the normal force. Now, I'm not going to be able to do this with the floor, but I could step into a special metal box that had a big steel cable, and that cable could pull up or down, or reduce or increase its tension, and that would change the normal force that I would experience. So, over the page here we have a lift, a metal box with which you can stand in. We call it a lift or an elevator. Okay. Now, we're going to ignore the tension in the cable. What we're going to look at are the forces on the person. So let's say that we had a 50 kilogram person. So I can say that his weight force is always down and it's 490. I'm just going to draw the forces off to the side here. Now, the normal force I'm going to draw in, but I'm not going to equate. Let's produce a change. Let's say that it accelerates at 2.0 meters per second squared upwards. So we're going to call it positive. Okay. So now he's no longer in equilibrium. We could say that the sum of all forces is ma, and that is the vector combination of weight plus normal. So it's no longer equal to 0. It's 50 by plus 2. So essentially, if somebody was standing outside of this lift and saw that gentleman accelerate upwards, and they knew it, they'd say, well, look, there must be an unbalanced force of 100 newtons upwards acting on that person because I'm seeing him, he's starting to increase his velocity upwards. There must be an unbalanced force. Well, if weight is locked in, then it must be that the normal force has increased. So therefore, the normal force equals 100, or minus. Well, we don't care. If I gave you the mass of the elevator, you could find the tension in the cable. But for now, we're just zooming in on this bloke. Okay, we don't care. The lift could be 5,000 kilograms. We don't know. Now, could I just get you to add this little note here? This is called apparent weight. That would be shown on the scales if he was to stand shown on scales. He feels as though his weight has increased. Okay? Now, get that written down. Increased with a D. If he was to go into the lift and put a set of scales down on the floor and stand on them, they would read 50. It presses the button, the lift accelerates up. While it's accelerating, the scales isn't actually measuring his weight. It's actually measuring the reaction force to his weight. It's actually measuring the normal force. Now, they assume that when someone measures their mass, that they're not in a lift. They're assuming that you're in equilibrium. And so it's just going to go weight equals an opposite to normal force. But it suddenly pushes up and the scales read 590 newtons. It might say that he suddenly weighs 59 kilograms, 58, 60 kilograms. Okay? He feels as though he's suddenly gained mass, but he hasn't. Okay? What you're feeling when you're sitting on your chairs or when you're standing, you're not feeling your weight. You're feeling the reaction force to your weight. You're feeling the normal force of the chair pushing back upwards on your butt. if you suddenly accelerated upwards, let's say your chair has a rocket underneath it and you accelerate upwards, you suddenly feel an increased reaction force. And all of a sudden you feel heavy. Okay? So, and this is only while you're accelerating. So remember, in a lift, the acceleration is two things. It's very small. It's a small acceleration. Or you'd have little old ladies getting into lifts in the shopping centre, and their knees would buckle and they'd collapse to the floor as the thing accelerates upwards. They've experienced 12 Gs. No, you're only experiencing 20% of gravity acceleration. You would feel 20% heavier for the instant you're accelerating. That acceleration only occurs for a small amount of time. Right? Or else you'd have lifts going up and down buildings at 100 kilometres per hour, and that doesn't occur. Okay? The fastest lift in Perth is in the BHP Billiton, and I think it gets up to about 30 kilometres per hour, because it needs to get people from the ground floor up to the 55th floor, and you know, you don't want to spend 5 minutes dawdling up a lift. So, while he's accelerating, he feels that his weight is 590. He feels as though his mass had suddenly increased by 20%. All right, but it's a trick. We can only feel the forces that act on us. Okay? So it's a bit weird, but I'll leave it there. Do I want you to have a look at homework?
9.
No?
9.
I'll give you some homework tomorrow, don't worry. We'll leave it there. Homework will come.